So, as an introduction of our laboratories, the nanotechnologies is a novel phenomenon in the nanoscales, and there are many applications, as you know well. And as an engineering, the measurement, observation technique, and application techniques and manipulation techniques are very important to realize device or some application, actual applications. So, and I come from the mechanical engineering. So, by using the mechatronics, we are very interested in micro machine or high density memory and biological engineer or manipulations. So, and this is like a territory map of the microscope. This is size is this direction is smaller, water-free, and leukocyte, and DNA and molecule. This is a optical microscope. The resolution is several nanometer due to the reflection limit of optical wavelengths. And scanning electron microscope, we can observe nanometer, but it requires vacuum conditions. There I talk about scanning for microscopes and its applications. And scanning for microscopes, you can use it not only in vacuum, but also liquid gas, air in the various environments. So it's a very convenient for the application in engineering field. So our laboratory will develop some manipulations. But the manipulation is not still well improved. So, and in our laboratory, we develop based on the scanning for microscope and improve for the manipulations for various applications. So maybe as you know well, many people know about the scanning for microscope, but today I talk about the instrument. So let me explain about the instrument. So scanning for microscope is a generic name of microscope using probes, and the surface property can be measured using very sharp probe by scanning. It has a nanometer scale of higher resolutions. So if you approach the probe and there are various interactions between probe and surface, what kind of surface property you want, it depends on what kind of probe and what kind of detector. By scanning the probe, you can obtain certain surface properties. And it's an individual names, but general name is a scanning for microscope. The most popular technique is the atomic force microscope. It's a 100 nanometer cantilever lens. The tip is 4 micron. The aperture is several 10 nanometer. So, and you can easily imagine this movies, and this is small. So, and by using movies, by using optical lever systems, and you can observe the deflection, and by using the feedback control from the movement of the surface, you can obtain the movement. And for the manipulations, the one if you use the strong interaction between probe and surface, you can fabricate the surface as fabrication of manipulations. So in our laboratory, we develop by ourselves. This is homemade force microscopes, and this is another function of the scanning microscope. In our laboratory, my student designs such a unique electrical circuit and software. So everything is constructed by ourselves. So we can develop for the model functions. So, and for example, this one is topography and optical image and time distribution. This image are simultaneously observed.
You might know liquid crystal is classified into two types. One is subtropic liquid crystal. This is very famous. Almost all audience use this every day. So subtropic liquid crystal liquid crystal phase is determined by temperature. But round liquid crystal is determined by temperature and concentration. So this relatively liquid crystal consists of two or more components. One component is amphiphilic molecules like surfactant or lipid and so on. And the other one is solvent molecules, waters and so on. So that big liquid crystal, typical example of liquid crystal is like this one. This is a liquid bilayer membrane. So you can see molecule here, like this one. Molecule has polar head and non-polar shape. The molecular shapes of amplified affect phase of liquid crystals. This is a type 1 molecular shape, which has big polar head and small non-polar shape. And then it forms like this type aggregate, spherical missile or cylindrical missile. Polar head toward outside and non-polar tails toward inside, and water locates outside. If cross section of polar head and non-polar tail is almost same, it forms bilayer membrane, like first try. And therefore, this next another type is type 2. It has small cross section of polar head and large cross section of tail, non-polar tail. It forms a small space, small polar space.
So multiferroic composite has special attention now, and in this case, for the case of multiferroic composite type multiferroic materials, so this is ferroic materials like PGT or barium titanate, or this nickel ferrite magnetic ferromagnetic layer is like layer by layer structures, or this kind of 1,3 type is in the barium titanate matrix, some nanopiller of cobalt ferrite nanopiller is standing like this. In this case, in this structure, both perovskite structures and ferrite structures, spinel structure is epitaxially grown on the substrate. So like this, and in this case, the special feature about the interaction is measured and reported in this report. And in this case, the electrode material is from the typical electrode is strontium ruthenium oxide or lanthanum strontium cobalt oxide or lanthanum manganese oxide and lanthanum nickel oxide or niobium doped strontium titanate. It's all these electrode is perovskite structure. And I'd like to say that all these perovskite structures electrode is not transparent. So, I'd like to classify the combination between the electrode and materials. In this case, there are many reports about epitaxially grown thin films. So, on the perovskite electrode, on the perovskite oxide, perovskite ferroic material is epitaxially grown. Okay, and on the perovskite electrode type electrode, and epitaxially grown from spinel ferrite is reported. And however, there are very few reports about the perovskite ferroic materials, spinel structure ferroic materials deposited epitaxially grown on the spinel electrode. There is almost no report. And so perovskite, this, as I said, perovskite transparent conductive oxide has not reported so far. But in some cases, the spinel type TCO, transparent conductive oxide, has reported. So my concept is using spinel TCO, all transparent novel devices will be fabricated. So this is for example, this in this case, this is a substrate and bottom electrode and magnetic layer or ferroelectric layer and upper electrode. If all these materials transparent, we can go through the light from the top of the back side of this thin film.